Fundamental Manufacturing Processes video series, examining the tools and techniques of precision manufacturing. This program explores the fundamentals of welding. Welding is a common method of joining metals and includes a wide variety of processes. These processes are used for many industrial applications, including the manufacturing of automobiles, aircraft, bridges, agricultural equipment, ships, machine tools, tube and pipe, tools and dies, fixtures, electronics, and medical products. An extremely important aspect of welding is joint design. The basic joint types used include the butt joint, the corner joint, the edge joint, the lap joint, the T-joint, the flanged butt joint, the flanged corner joint, the flanged edge joint, the flanged lap joint, and the flanged T-joint. The portion of the joint where the members to be welded are closest to each other or meet is the joint root. This may be a point, a line, or an area. Depending on the welding process, the joint root may be closed or open with a controlled width gap to assist weld penetration. Joints may also require some type of edge shape to allow for complete joint penetration during welding. The basic edge shapes include square, single bevel, double bevel, single J, double J, flanged, and round. Depending on the welding operation, edge shapes are combined to produce the desired weld. When selecting a welding process for specific applications, many factors must be considered, including the materials to be joined, the thickness of the parts, the joint design, the joint location and orientation, edge preparation, weld bead quality, production requirements, equipment cost, equipment portability, environmental requirements, welder or machine operator skills, and safety considerations. The numerous welding processes join or coalesce metals together by either fusion welding or solid-state welding. In fusion welding, metal coalescence is created by melting a base metal and filler metal together, or by melting the base metal alone. The principal fusion welding processes are arc welding, resistance welding, laser beam welding, and electron beam welding. Arc welding processes use an electric arc as the heat source to melt and join the base metals. The arc is struck between the workpieces and the tip of an electrode. Arc welding electrodes are usually consumable, but can be non-consumable. The consumable electrode is usually wire or rod, and the current that sustains the arc also melts the electrode so that it supplies filler metal to the joint. The electrode may also produce a slag covering to protect the hot weld metal from oxidation. The most common non-consumable electrode is a tungsten rod, which carries the electric current. If a welding operation using a non-consumable electrode also requires a filler metal, it is supplied by a separate wire, rod, or consumable insert. While welding, the electrode is moved either manually or mechanically along the joint, or the electrode is held stationary and the workpiece is moved. Arc welding encompasses a variety of processes, the primary types being shielded metal arc welding, submerged arc welding, gas metal arc welding, flux cord arc welding, gas tungsten arc welding, and plasma arc welding. Shielded metal arc welding uses a covered electrode consisting of a core wire surrounded by a concentric covering, which is a mixture of silicate binders and powders. These binders and powders serve as a source of arc stabilizers, fluxing agents, lubricants, gases to displace air, and metal and slag to protect, support, and insulate the hot weld metal during welding. The bare section of the electrode is clamped in a holder, which is connected by a welding lead or cable to a terminal of a constant current power source. The workpiece is connected to the other power source terminal. Touching the tip of the electrode against the workpiece and withdrawing it slightly initiates or strikes the arc. The heat of the arc melts the base metal in the immediate area as well as the electrode core wire and covering. The molten base metal, core wire, and metal powders in the covering coalesce or fuse to form the weld. The equipment required for shielded metal arc welding includes either an alternating current or AC, or direct current or DC power source, welding leads, an electrode holder, welding helmet and gloves, and protective clothing. The process is effective for welding ferrous metals such as cast iron, carbon, low alloy, stainless, and tool steels, and non-ferrous metals including copper, nickel, aluminum, and their alloys. In submerged arc welding, a bare, continuous consumable electrode wire, shielded by a layer of granular flux particles, sustains the arc. When the arc is struck, the tip of the electrode is submerged in the flux, and the arc is not visible. Welding proceeds without the intense radiation that characterizes open arc processes, and with little fumes. The submerged arc welding process varies from semi-automatic to fully automatic. Equipment includes automatic wire feed devices and joint tracking systems to move either the welding head or the workpiece. Submerged arc welding is commonly used to join all types of steel, stainless steels, and nickel alloys. Gas metal arc welding uses a continuous solid wire electrode for the filler metal and a shielding gas to provide the desired arc characteristics and protect the molten weld metal from air. Gas metal arc welding is suitable for welding many types of joints of most any metal in all welding positions. The characteristics of the gas metal arc welding process are best described in terms of the three basic modes by which metal is transferred from the electrode to the work: the short-circuiting transfer, the globular transfer, and the spray transfer. The type of transfer is determined by a number of factors, the most significant including the magnitude and type of welding current, the electrode diameter, the composition of the electrode extension or length, and the type of shielding gas. The short-circuiting transfer mode encompasses the lowest range of welding currents and electrode diameters associated with gas metal arc welding. Metal is transferred from the electrode to the work only during intervals of controlled short circuits. The short-circuiting transfer mode is generally suited for joining thin sections, bridging large root openings, and for welding in all positions. The globular transfer mode is characterized by drop sizes with a diameter larger than that of the electrode. These molten drops are easily acted on by gravity, usually limiting successful transfer to the flat position. The spray transfer mode deposits small droplets of metal at rates of several hundred per second. Spray transfer requires high electric current and argon or argon-rich gas mixtures to shield the arc. Metal transfer is stable, directional, and virtually spatter-free. Flux cord arc welding uses a filler metal made up of a tubular electrode with a flux core and with or without additional gas shielding to join carbon steels, low alloy steels, stainless steels, and cast iron. The core may contain minerals, ferroalloys, and ingredients that provide shielding gases, deoxidizers, and slag-forming materials. These ingredients promote arc stability, enhance weld metal properties, and improve weld bead contour. Gas tungsten arc welding uses a non-consumable tungsten electrode and externally supplied inert gas shielding. The most common shielding gases used are argon and helium, and mixtures of the two gases. All types of steels and most non-ferrous metals can be welded in all kinds of joints and positions. Depending on the application, workpieces can be welded without a filler metal or welded with a filler metal supplied separately to the joint. The gas tungsten arc welding process employs either an alternating current or direct current power source, depending on the type of metal to be joined and its thickness. Some power sources provide pulsating direct current at a frequency. These adjustments allow better control of the molten weld metal when welding thin sections and when welding in other than the flat position. In plasma arc welding, metal coalescence is produced by a constricted arc made up of a high-velocity stream of ionized gas called a plasma. In most plasma arc welding operations, the plasma jet is generated by heating the orifice gas in the torch polenum chamber to a plasma and forcing the plasma to exit through a constricting nozzle or orifice. Partial shielding is obtained from the plasma and is supplemented by an auxiliary shielding gas. Auxiliary shielding gases used include argon, helium, or mixtures of argon with hydrogen or helium. Because of the constricted arc, the heat energy of the plasma stream is concentrated and extremely intense. This permits deep penetration, narrow welds, and rapid welding speeds with good arc stability. Workpieces can be joined with or without filler metal. Plasma arc welding can be used to join most ferrous and non-ferrous metals, including extremely thin materials such as foils. Plasma arc welding equipment cost is high, however, so the process is often limited in its application. Resistance welding processes produce coalescence of overlapping workpieces with heat generated by the resistance of the workpieces to the flow of electric welding current and the application of pressure. Resistance welding is primarily used to join sheet metal stock, but is sometimes used to join thin plate. All metals which can be fusion welded are weldable by resistance welding. Resistance welding processes use copper electrodes. These electrodes perform 4 functions. They conduct the welding current to the work and, in some cases, fix the current density in the weld zone. They transmit a force to the workpieces. They dissipate some heat from the weld zone. And they maintain relative alignment and position of the workpieces in some resistance welding operations. Very high electric currents are used to quickly produce the resistance heat necessary for fusion. The three principal types of resistance welding are spot welding, seam welding, and projection welding. Spot welding refers to making welds one at a time between the electrodes. One, several, or many individual spot welds may be required, depending on the application. Spot welding, with the electrodes maneuvered by articulated arm robots, is commonly used to join sheet components of automobiles. In seam welding, coordinated pulses of electric current from rotating wheel electrodes produce a series of overlapping spot welds, resulting in a leak-tight welded joint. In projection welding, the welds are localized at predetermined points by projections, embossments, or intersections. Several points may be welded simultaneously. All resistance welding methods use either semi-automatic or automatic systems. With semi-automatic machines, the operator either positions the workpieces between the electrodes or positions a portable welding gun around them and pushes a switch to initiate the weld. Welding then proceeds according to a pre-programmed sequence. Automatic machines feed workpieces into the machine, where they are welded and then ejected without operator assistance. The typical resistance welding system consists of a control panel, a welding machine with a rigid frame, a low-voltage, high-current welding transformer, electrodes, leads connecting the electrodes with the welding transformer, controls to regulate electric current, and a pneumatic cylinder or other means of exerting force to the upper electrode arm. In laser beam welding, the heat for coalescence is generated by a focused beam from a gas or solid-state laser. The most commonly used gas laser is the carbon dioxide or CO2 laser, which is actually a mixture of carbon dioxide, nitrogen, and helium gases. The most commonly used solid-state laser is the neodymium-doped yttrium aluminum garnet, or YAG laser. CO2 lasers can generate greater continuous beam power and are suitable for welding thin or thick workpieces. YAG lasers generate less continuous beam power and are generally used to weld thin workpieces. Most laser welds require no filler metal, although filler metals can be used if desired. Inert shielding gases are normally employed, usually argon, helium, or a mixture of the two. Welding speeds are usually much higher than other welding processes, thus limiting heat-affected zone size and workpiece distortion. In addition, because of the intense, precisely focused heat, welds can be quite deep. Also, welds can be made in confined regions and between dissimilar metals. Laser beam welding systems are used in many industries and are typically fully automated and computer controlled. Typical equipment includes the laser and its power supply, a beam delivery system with mirrors and focusing optics, a workstation, and a motion control system to move either the laser beam or the workpiece. Many ferrous and non-ferrous metals can be joined using laser beam welding, including carbon, alloy and stainless steels, aluminum alloys, copper alloys, magnesium alloys, nickel alloys, titanium alloys, and refractory metals. In electron beam welding, the coalescence heat is generated by the kinetic energy of a focused stream of electrons directed upon the joint. The electrons are produced by an electron gun, accelerated to high velocity, shaped into a beam by electrical fields, and then further collimated or made parallel and focused by an electromagnetic lens. This electron stream is developed in high vacuum, but actual welding can be performed in either high vacuum, partial vacuum, or standard atmospheric pressure. Because of the intense and concentrated heat generated, total heat input is low, minimizing heat-affected zone size and part distortion. This also allows for the creation of extremely deep and narrow welds. Additionally, joints inaccessible by other welding processes can be welded. Virtually all ferrous and non-ferrous metals, thin or thick, can be joined. Welding speeds are fast, and filler metal is not generally required. Equipment cost for electron beam welding is typically high, and welding is generally limited to machined parts assembled in primarily butt, corner, and lap joints. In solid-state welding, coalescence is created at temperatures less than the melting temperature of the base metals with pressure. The two most used solid-state welding processes are friction welding and ultrasonic welding. Friction welding is an extremely rapid method of welding workpieces, typically in butt joints, by frictional heat and axial force. Frictional heat is generated by rapidly rotating a workpiece against a stationary workpiece until the interfacing or faying surfaces reach the proper temperature. The weld is completed by an upsetting operation which consists of the rapid application of additional axial force as or just after the rotation stops. This upsetting operation forces hot metal, oxides, and impurities out of the joint. In general, one workpiece must have an axis of symmetry and be capable of being rotated about that axis. Workpieces are usually either in butt or T-joints, with the pieces being bar to bar to tube, tube to tube, and bar or tube to plate or disc. Additionally, friction welding can be used to join a wide range of similar and dissimilar materials, including most metals and alloys, some metal matrix composites, ceramics, and plastics. Ultrasonic welding is a method of producing lap joints by high-frequency vibratory energy and moderate force. This induces interatomic attraction and metallurgical bonding at the weld interface surfaces with relatively little heat. The workpieces are clamped between two welding tips called sonotrodes or jaws. Vibratory energy is conducted through one or both tips, which oscillate laterally as a perpendicular force ensures contact of the workpieces. The oscillating action disrupts the interface surface films and permits metal-to-metal contact. This creates plastic deformation at the interface, resulting in a solid metallurgical bond. Under proper conditions, interface temperatures reach only 35 to 50% of the workpiece melting temperature. Basic equipment includes an electric power supply, a frequency converter to increase line frequency to generally 15,000 to 75,000 hertz, one or more transducers to convert that power into acoustical power of the same frequency, a coupling system to transmit the acoustical power to the welding tip and into the workpieces, a workpiece support system, and a force application system. Ultrasonic welding typically requires at least one of the workpieces to be thin. The usual welds are spot welds and straight or circular seam welds. Workpiece distortion is limited. Ductile metals in similar or dissimilar combinations are ideal workpieces, although hard metals also can be welded. Filler metals are not normally required, although they can assist in joining difficult-to-weld dissimilar metals. The electrical and electronics industries are the principal users of ultrasonic welding. Limited applications are also found in the automobile, nuclear, and aerospace industries. Let's review the material contained in this videotape. Welding is a common method of joining metals and includes a wide variety of processes. These welding processes join metals together by either fusion welding or solid-state welding. In fusion welding, metal coalescence is created by melting a base metal and filler metal together, or by melting the base metal alone. The principal fusion welding processes are arc welding, resistance welding, laser beam welding, and electron beam welding. Arc welding processes use an electric arc as the heat source to melt and join the base metals. The arc is struck between the workpieces and the tip of an electrode. Arc welding encompasses a variety of processes, including shielded metal arc welding, submerged arc welding, gas metal arc welding, flux cord arc welding, gas tungsten arc welding, and plasma arc welding. Resistance welding processes produce coalescence of overlapping workpieces with heat generated by the resistance of the workpieces to the flow of electric welding current and the application of pressure. The three principal types of resistance welding are spot welding, seam welding, and projection welding. In solid-state welding, coalescence is created at temperatures less than the melting temperature of the base metals with pressure. The two most used solid-state welding processes are friction welding and ultrasonic welding.